Okay, now we are going to talk about probability theory, the very basics of probability theory. All right, so here's how we create the probability space. First of all, we talk about the outcomes. So for any experiment, let's denote all possible outcomes as set omega, all right? And so a standard element from this set omega is W, all right? So W is an outcome. So for example, when you toss a coin, it's going to be either head or tail, right? There's no other outcome. So W is either head or tail. So there are two outcomes. If you toss a dice, for example, it's going to be either 1, 2, 3, 4, 5, 6. So these are the outcomes, etc. Then we talk about collection of all subsets of outcomes. All right, that basically tells us the event set. So script A is the set of all the subsets of all outcomes. So it's basically 2 to the power omega minus the empty set. So it's all non-empty subsets of omega. The script A. And then the probability measure. All right, so what is the probability of every event in this set? So event is denoted sometimes E. I'm going to use the notation A here. An event, which is basically a subset of the omega, so possible outcomes. For example, if it is head or tail, remember tossing a coin. So if I toss a coin one time, well, then there are, two possible events. Event one is where the coin comes up head, and event two is the event where the coin comes up tail. So head or tail. So there are two possible events. If, however, I toss the coin twice, well, then there's more than two possible events. And the probability measure is, what is the likelihood of each event in the set script A. All right, so therefore, omega, script A, and P defines the probability space. So example, if we are talking about rolling a dice, so there are 6 possible outcomes. There's no more, if it is a normal dice, well then the set of all non-empty subsets of the outcome set omega is basically 1, the singleton 1, 2, 3, 4, all the way up to 6, and then doubletons 1, 2, 1, 3, 2, 3, etc. So 5, 6, and then the whole set of outcomes. All right, so the P is, we call it, it's a probability of all sets or events. A P cannot be any random function on set of events. So it has to satisfy these 3 properties. All right, so any measure, probability measure, has to satisfy these 3 properties. 1, for any event A, all right, so for any A in script A, the probability of the event has to be non-negative, first of all. I mean, what is the likelihood of something happening is negative 2? Make no sense. It has to be positive. It has to be non-negative. It can be 0, obviously. The thing is, the probability of all the possible outcomes happening, all right, has to be 1. Right? I mean, which means is like probability of something outside of the possible outcomes is not possible. All right. So I'm sorry, it wasn't so clear maybe, but the universal set, which is omega, universal set of outcomes, its probability has to be 1. And the third thing is that if there are 2 disjoint events, all right, so I have an event A, I have an event B, their intersection is empty, let's suppose, well then the probability of A union B has to be equal to probability of A plus probability of B. The third condition, along with the others, it actually implies in general, I mean for any event A and B, we have to have this inequality. Probability of A union B is less than or equal to probability of A plus probability of B. Okay, so let's talk about conditional probability. So suppose that A and B are two events, and then we define a conditional probability, the probability that A is occurring conditional on B is true. It's defined by the probability of A intersection B divided by probability of B. All right, so assuming that probability, so the event B is likely, so the probability of B is non-zero. All right, so this is how we define conditional probability. Probability that event A occurs conditional on event B is true. We sometimes call probability of A and probability of B's as marginal probabilities. All right, so what is independence? So two events are independent means the conditional probability of event A conditional on B is true is equal to probability of A. All right, so what does that mean? That means B's occurrence actually provides me no information about the likelihood of A. All right, so B's happening is not going to give me new information about A. So therefore, probability of A and probability of A conditional on B are going to be the same. All right, so the Bayes rule is basically sort of a reverse conditional probability. All right, so given probability of A conditional on B, I can calculate probability of B conditional on A. How do I do that? Well, so this is sort of a simple conversion formula. It says the probability of B given that event A is true is equal to probability of A given that event B is true times probability of B divided by probability of A. Okay? So, basically you can see the equality here. The probability of A given B is probability of A intersection B divided by PB. So PB's will cancel out. I'm going to have probability of A intersection B in the nominator, and so here, and then in the denominator I still have PA, so therefore PB slash A is nothing but probability of A intersection B divided by probability of A, sort of symmetric to this one. All right, we are going to use the Bayes rule when we talk about expected utility, for example. All right, so now let's talk about a bit about random variables. So random variable is actually a function. All right, so let's talk about a real valued random variable. So RV means random variable. It basically maps every outcome to a real number. All right, so every outcome corresponds to a one and only one real number. So that's it. So a random variable is just a function between set of outcomes to set of reals. Well, because the probability measure P is a measure on a set of all events, well then it actually induces also probability on the random variable X. For example, how can I calculate the probability of my random variable, supposing that it's a real valued random variable? How can I calculate the probability that my random variable is non-negative? Well, I can do it as this way. Well, first of all, what does that mean that my random variable is non-negative? Well, it actually means all possible outcomes where my random variable maps it to some real number which is non-negative. All right, so maybe there is no outcome where my random variable maps it to a positive or non-negative number. So this set might be empty. Well, be careful. So therefore, I can sort of relate the set of the cases where my random variable is non-negative to a set of all possible outcomes where my random variable is mapped into a non-negative number. So this creates an event, and I know how to calculate the probability of event because P is a probability measure. So it basically tells me what is the probability of that event. So the probability of this event is therefore equivalent to the probability of my random variable being non-negative. So this is how we relate probability on a random variable to our probability measure over the set of events. Okay, so now let's talk about cumulative distribution functions. All right, so for a real valued random variable, the probability of my random variable being less than or equal to some parameter x is a function of this parameter x, and we call it a cumulative distribution function of x, and we denote it by f subscript capital X of x. Right? We sometimes just ignore capital X if it confuses you. So this is a cumulative distribution function of x. Well, the random variable x. Well, the thing is why we call it cumulative distribution function, because it basically tells me the probability of random variable being all the way up to some level x, all right? So sort of a cumulatively, well, remember x is a real valued random variable, so the value of x is either less than x or more than x, and so this probability tells me that this random variable will always, not always, the likelihood of this random variable taking values lower than x. So sort of I accumulate all those probabilities all the way up to x. So we call it cumulative distribution function, CDF. All right, so given two real numbers, x1 and x2, these are real numbers, all right, where my random variable will probably be less than or greater than. So we calculate the probability that my random variable is being in the range of x1 and x2 as follows. So it's basically the cumulative distribution, cumulative probability of my random variable is, remember x1 is less than x2, so cumulative probability of being less than x2 minus cumulative probability of being less than x1. All right, so it's basically the probability of my random variable is less than x2 and minus probability of my random variable is less than x1. So therefore it has to be in between this range. But be careful, this probability, this term is equivalent to this term, where here the inequality is strict, not equal. If x is a continuous random variable, this doesn't make any difference. However, if it is a discrete random variable, well, then this is very important whether we have equality sign here or not. So this, we don't have equality. Why is that? Well, if you think carefully, the event that the random variable x is less than x2 can be written as two disjoint events where, remember, x1 is less than x2, so x is going to be less than x1. All right, union, x is greater than x1, but less than or equal to x2. Here, I put this inequality here because I already counted those cases here, right? If x is equal to x1, it's included in this sort of event set. So therefore, I don't want to double count those cases where x is equal to x1. So because of this, I start my equality as inequality here, all the way up to x2. x2 is included. So because these two events are independent, the probability of this is equal to probability of this plus this, right? And therefore, the probability of this thing is equal to this minus this. And hence, well, by definition, it's equal to this term. If, however, my random variable is continuous, all right? By the way, this is possible only if my outcome set omega has continuum of alternatives. And so if my random variable is continuous, well, then we assume that the limit as delta approaches to 0, fx x plus delta minus fx x divided by delta, which is indicated as p sub capital X of x, exists. Well, what does that mean? Well, if you remember our previous notes, this is nothing but the derivative of the f function, the CDF function. So we assume that the CDF function, the cumulative distribution function, is differentiable at point x. If it is differentiable, so this is sort of the slope of the CDF. And we call this, by the way, if the CDF function is everywhere differentiable, well, then we can talk about this pxx function, and this function is what we call PDF, probability distribution function of a random variable x. And thanks to fundamental theorem of calculus, we can actually write the CDF, again, you can ignore this x, the CDF, the f of x is always equal to an integral all the way from minus infinity to x, all right, p x dx, all right? So be careful, the probability, so when your random variable is continuous, the probability of one exact point occurring may be 0. And in fact, if it is continuous in the sense that there's no discrete jumps, well, then it has to be 0 for all x's. So therefore, I cannot calculate the probability of x being equal to some x1, but the thing is, I can calculate, so that probably is 0. As I said, the distribution function, the PDF is continuous, all right? I'm not talking about continuous random variable. The random variable can be continuous, but the PDF does not have to be continuous, all right? So they're two different things. So the probability of x equals x1 is equal to 0 when I have a continuous probability distribution function. But I always can write the probability of my random variable taking a value in some range between x1 and x2. All right, and this probability, thanks to the fundamental theorem of calculus, can be actually written as an integral all the way from x1 to x2, p of x dx. All right, so here the important point is I have this strict inequality, but again, if my PDF is continuous, this doesn't make any difference, but nevertheless, be careful. Here, this is not true, I mean, this is x1 less than or equal to x less than or equal to x2. This is not necessarily equal to this one, as the arguments sort of indicated here. The double counting of x1 may cause problems if the probability of x1 is positive. And in discrete case, this is usually the case. In a continuous case, when the PDF is not continuous, this might be the case. So therefore, be careful about those boundary issues. Okay, so finally, let's talk about very briefly expectation. All right, expectation of a random variable. So if my random variable x has a probability distribution function p of x, well, then the expectation of f of x, so f is just any function of x, for example, x squared, x plus y, etc. So then the expectation of the function f of x, well, I mean, a function of a random variable generates another random variable. So the expectation of f of x is therefore integral f of x px dx, all right? So this is the PDF and this is the function. So if x is a discrete random variable, however, the expectation is a finite sum instead of a continuous sum. So it's a finite sum, f of xi, well, the probability of x is being equal to xi, all right? So as a special case, when my f function is the unit function, so f of x is equal to x, well, then we call the expectation of x as the mean, and the expectation of x minus expectation of x squared is what we call variance. All right, so we are going to use expectation. It's a very important part of economic theory, is expected utility theory. We're going to use it a lot. So f is going to be our utility function in those scenarios. And therefore, basically, we can calculate. So these are nothing but expected utility calculations. So the expected value of a random variable is basically tell me the probability of your random variable times the value of your random variable. So your random variable can take values 5, 3, 7, minus 8, whatever. And so tell me the value of your random variable times its probability. Well, in the discrete case, it makes more sense. Plus the probability of another value, potential value of your random variable times that value, plus etc. All right, so when we this is a weighted average of your random variable, okay? So let's suppose I give an exam, and in the exam, there are like 5 students getting, I don't know, 90 out of 100, 10 students get 50 out of 100, etc. So I have some distribution, and then I calculate the mean, right? So I calculate the average. So it's like the likelihood of being my random variable 90 and the likelihood of my random variable being 50, and then I multiply those with 50 and 90 because these are the values of my random variable, and then so the weighted average is going to give me, okay, I gave that exam and the average of this classroom, I can't specifically tell this student got this student got that, but the average grade is whatever. So that's the idea of expectation.